Let us now look at some examples of games and Nash equilibria in those games. So here's the first game, a familiar game. This is, of course, the prisoner's dilemma. If both prisoners cooperate and then they get a light punishment, and if they do not cooperate, they get a more severe punishment. If the one cooperates and the other does not, then the cooperator gets a terrible punishment, and the one that does not cooperate gets off scot-free. Now, of course, this game has a dominant strategy to defect. No matter what the other agent does, you're better off not cooperating. And so, of course, the only dominant strategy outcome is this one of both defecting. And indeed, that is the only Nash equilibrium in this game. So it's a Nash equilibrium. It's the best response. If the other person defects, then it's the best response to defect. But in fact, it's much stronger than that. It's best to defect no matter what the other agent does. So this is an example of one unique Nash equilibrium that happens to be a very strong one, a dominant strategy, Nash equilibrium. So here's another game. This is a game of pure coordination. Think of it as walking towards each other on the sidewalk, and you both can decide whether to go to your respective lefts or your respective rights. In both cases, you will do fine and you will not collide. And of course, if you miscoordinate, if one goes to the left and the other to the right, you will collide. So this is a natural game, and in fact, you see that you have two Nash equilibria. The one that I wrote down here. If one of the players goes to the left, it's the best response to go to the left, and conversely, if the other player goes to the right, you're best off going to the right as well. And the others are not Nash equilibria. So here's an example of a game where there are two Nash equilibria, or two specifically pure strategy Nash equilibria. Again, we'll discuss why we call these pure strategy later on. Here's a very different game. This is often called the game of Battle of the Sexes. Imagine a couple, and they want to go together to a movie, and they're considering two movies. One of them a very violent movie, Battle of the Titans, and the other a very relaxed movie about flower growing, called these B and F. The wife, of course, would prefer to go to Battle of the Titans, and the husband would prefer to watch flower growing. But more than anything else, they would want to go together. And so here are the payoffs. If they both go to Battle of the Titans, then they're both positively happy, the wife more than the husband. If they both go to the flower growing movie, then the husband is slightly happier than the wife. But if they go to different movies, neither of them is happy. That's the game. How many equilibria do we have here? Well, again, we have two pure strategy Nash equilibria. Why is that? Well, if either of them goes to the Battle of the Titans, then the other one would want to go there too, because if they go to a different one, they would get 0 rather than whatever they get here, 1 or 2, depending on whether they're husband or the wife. And conversely, on the flower watching movie, flower grow movie. And so in both cases, the best response is to go to the movie selected by the other party. So on the face of it, it looks very similar to the game of pure coordination that we have here, but we do see a slight difference here, and we'll revisit that later on when we speak about not pure strategies, but mixed strategies. Here's another example, the last one we'll look at, and this is the game called Matching Pennies. Imagine each of us, two players, needing to decide on some side of a coin, heads or tail. If we decide on the same sides, heads or tail, but we decide on the same one, then I win. If we decide on different sides, you heads and me tails, or vice versa, then you win. And so we see this here. If we both decide on heads or we both decide on tails, I win, and otherwise you win. By winning, I mean I get 1, you get -1. So this is a zero-sum game. The sum of our payoffs is 0. What is a pure strategy Nash equilibrium here? Well, let's think about it. Suppose I pick head. What is your best response? Well, your best response then is to pick tails, because you get 1 rather than -1. But if you pick tails, then my best response is now to play tail, because I want to coordinate with you, because then I will get 1 rather than -1 that I would be getting here. But now if I play tails, you'd rather play heads, because you'd get 1 rather than the -1 you're getting here. But again, if you're playing tails, if you're playing heads, I want to play heads to match. So we have this cycle where the best responses are leading us in the cycle. And so there is no pure strategy Nash equilibrium in this game of matching pennies.